In today's video, we're going to cover AND gates, and I've got 4 of them. These 2 were in the grab bag, and these 2 were ones that I already had. Here, let me explain why. So this first one is a little surface mount component, and it's a quad 2 input AND gate. And like I mentioned, using these surface mount ones on a breadboard is just too difficult. So what I did was I grabbed one that I actually had, which is the same. This is also a quad 2 input AND gate, and that's the one we're going to use in the breadboard. This is another one that was in the grab bag, and this one right here is a dual 4 input AND gate, and we'll take a quick look at that here in a minute. And then this last one's a little bonus one. This one is actually a NAND gate, and I'll explain that as well. This also was not in the grab bag, but I thought it was interesting to include as part of this video, so I went ahead and brought it out. So before we get started, let's take a look at what the AND gate looks like, and it's going to be this little guy here, and it's got 1 output and 2 inputs, and we can just call these A, B, and O. And this is the symbol for the AND gate, and it's pretty much exactly as it sounds. If A and B are high, then the output is high. If either of these are not high, then the output is low. So that truth table would look like A, B, out. So if this was high, high, then the output is high. If this were to be high, low, the output's low, low, high, low, and low, low would also be low. So pretty self-explanatory. Let's also take a look at the NAND gate, and that's going to be essentially the opposite. So the symbol looks like this, and it's got this little 0 or dot here, which indicates that this is not or inverted. And this is going to be if both of these are high, then the output is low, and pretty much every other condition is going to be high. So its truth table is going to look like this. So if this is high, high, then the output is low. If this is high, low, this will be high, low, high, high, and then low, low will also be high. So as you can see, it's essentially just the exact opposite of our AND gate. The first one is that little surface mount guy, and this is going to be a quad 2 input AND gate. And as you can kind of see from the little circuit diagram here, it has 4 in the package, and there's 2 inputs and then an output, and then 2 inputs, output, and so on. So pretty straightforward. That's where the quad comes from, that there's 4 of them. 2 input means there's 2 input. So this one doesn't have a whole lot of information on the data sheet, but let's take a look at the one that's in a little dip package. And this is that second one. This is the quad 2 input, but in a dip package. This is a different manufacturer, but it operates exactly the same, and the pinouts are the same as well. Another interesting note on this one is it does have a relatively large voltage range between 3 and 18 volts. This is that third one, and this is going to be that dual quad input. So what that means is there's 4 inputs instead of 2, but then subsequently there's only 2 within the package since it's still the same exact size. So this is the data sheet for that. This one also has a large voltage range between minus 0.5 volts and 18 volts. And one other interesting thing is the input and the output current are about 10 milliamps. So you could just get a LED to blink or run off of an output, but not a whole lot more. So if you needed to run a higher load, you'd have to put in some type of a transistor. And here's what that dual 4 input looks like. It's organized a lot different on the chip. You can see there's 4 inputs, and this is going to be 2, 3, 4, and 5, and then it's got 1 input on, or output on pin 1. And here it is on the chip output right here, and you can see there's 2 pins that are actually not connected or not used for anything. And here we go. We've only got the 2 on that, but we've got 4 different inputs. And lastly is going to be this quad 2 input NAND gate that I had. And as I mentioned, here's that circuit diagram or the logic diagram, and it's got that little circle on it. And this one, the Texas Instruments datasheet kind of dives in a little bit deeper on some of the applications. So what were these things used for? The bottom line is pretty much anything. You've got to remember, before we had microcontrollers, in order to check if 2 things were true or 2 things were false, we really needed to use some of this type of logic, some of these little logic gates. And so the bare computers would be made up of just dozens of these little ICs that would just walk through that different logic. But anyway, they're still today used in a lot of different components. And the pinouts are very similar to the first one, the AND gate. We've got A and B, and then the output, A, B, output, and on 2 on one side and 2 on the other side. And then here's a nice little table explaining all of them. I'm going to take a look at this page here real quick, and we're going to test this out on the oscilloscope for each of them. But this one has a recommended supply voltage of 2 to 6, nominally at 5. This was kind of designed about the time where a lot of controller boards were running off of 5 volts. And one of the other things you'll notice right here is going to be this input transition rise and fall time, and we're going to be operating it at about 5 volts. So we'll look at about here at 500 nanoseconds. And so we'll take a look and see if this can hold up at about 500 nanoseconds on the oscilloscope, and we'll see how that waveform looks. There we have it on our breadboard. We've got our AND gate, we've got our 1 input and our 2 input, and then our output is just this blue LED with a little resistor on it. Here's our ground, and then here are 2 switches just as we've been wiring them up. So they're normally closed, so both of these are low and our output is low. So if we push one of them and take that high, our output is still low. If we take the other one and put that high, the output is still low. If we put them both high, then the output is high. And so that's exactly how it's supposed to work. It's an AND gate, so if both of these are high, then the output is high, otherwise it is low. So that might not be super interesting or exciting. Obviously, we could do this with just some simple switches, but the one thing that we want to do now is let's take this over to the oscilloscope. Let's pump these 2 inputs in through very high frequencies and see how well the output keeps up with it and if it starts to fall apart. So I have the AND circuit on the oscilloscope, and you can probably even see that LED blinking on the camera. Now I've got a little board here that I'm working on, and it's not completely done yet, and the numbers on the board here are actually completely wrong. I just am printing something to the screen, so that is not the frequency that this is putting out, but everything else on it works. And right now I've got it scaled way back, and if you take a look at the oscilloscope, you'll see it's running at about 30 hertz, which is why you can kind of see that LED blinking on and off. So let me zoom out a little bit and we can kind of see how that AND works. So the bottom line, the blue line, is our output, and then inputs 1 and 2 are yellow and pink. Now, as you can see, since it's AND, both of them have to be high for the output to be high. And at this really low frequency, you can see it's keeping up just fine. So let's go ahead and increase that frequency and see how it does. So now we got the frequency at about 31 kilohertz, and as you can see, it's functioning just fine. It's keeping up with it just fine. So let's go ahead and ramp this up closer to 1 or 2 megahertz. Now we've got our primary frequency at about 5.3 megahertz on the yellow, and then the pink is exactly half of that, and then the blue is our output. And as you can see, it's actually keeping up pretty well. I mean, it doesn't have a nice little square wave. It's much more of a little triangle, but in all practical purposes, I would say that is keeping up well within the specs of the scope. This is actually 200 nanoseconds. I'm not sure if the datasheet said specifically what the frequency on that was that it supported. So with this test, channel 2 is exactly half the frequency of channel 1. Let's change it so that it's completely out of sync, and we're going to adjust a little PWM circuit for the second input and see how well that handles. So now what I'm feeding in is on channel 1, or yellow, on my input is a standard frequency of about 65 hertz. And then on the second channel, the pink channel, is another frequency of about 61 hertz, but it's a PWM signal. And as you can see, it's fluctuating a little bit, causing our output to also fluctuate quite a bit. And as you can even see, the LED is kind of blinking in a weird little pattern, but it is definitely blinking, and it appears to be keeping up. Now let's do a single shot capture so we can actually see what's going on here and verify that everything is working fine. Let's zoom out a little bit, and now we can zoom in. And now remember, this is the AND gate, so the output, the blue line, will only be high if both the pink line and the yellow line are both high. And as you can see, at this extremely low frequency, everything is keeping track just fine. Let's go ahead and ramp that frequency up and see what happens. So now I've got channel 1 coming in at about 67 kilohertz and channel 2 at around 62 and a half kilohertz. And as you can see, there's a lot of kind of movement on the scope. We'll just go ahead and pause that so we can zoom in real quick. And now you can see here, much faster, you can see where we get some little indications where both lines go high briefly and then drop again. And you can see right here is where they're no longer covering on the two outputs, but you can see there's just a really light little bump right there on that one. So at 67 kilohertz, it appears to be running fine. Let's crank it up a little higher. So here we're running at about 5.3 megahertz on the first channel. Let's go ahead and pause that and we can zoom in and take a look at it. Now let's look at this little peak here because it seems to be pretty consistent. And so you can see that second channel went low for a cycle, and you can see the output followed along just fine. So even up at 5.3 megahertz, this appears to be keeping up just fine. So there you have it. I'm going to say that the AND gate is successfully running easily at 5 megahertz without any significant problems. On this quad 4 input AND gate, I wanted to mention one thing on the data sheet is that on pin 7, it says VSS instead of ground. Now, I believe this stands for voltage source sink, and then it says voltage D or VDD for the 5 volts or the positive voltage. I forget what the VDD stands for, but anyway, this is going to be our 5 volts, and this is going to be our ground. I have this wired up on the breadboard, so let's take a look. All right, I've got this wired up on this breadboard. It's a little bit more of a mess versus the other ones, mostly because I've got 4 switches and each one of them needs 3 wires. And right here, I've got that dual 4 input chip, and they're kind of color coded. So I've got my 4 green wires, which are my inputs, and those are going into pins 2, 3, 4, and 5. And then I've got my blue LED on pin 1, which is my output. And then I've got my 4 switches. So it's a little bit hard to push those switches, but technically if any 1, 2, or 3 of them are pressed down, the LED should not light. But if all 4 of them are pressed down, then the LED will light. Again, it's an AND gate, so everything has to be true in order for the output to be on. And there we have it. So I think we'll take this over to the oscilloscope and take a quick look at that and see how fast it can keep up. I have not tested that on this chip, so I don't know what to expect. Now I've got that dual quad input, so this has 4 inputs, and right now I just have 2 of them, pins 3 and 4, or I should say inputs 3 and 4, just tied to high, so it's technically just a quad, or it's a dual input, which is going to be the 2 signals, the yellow and the purple on the oscilloscope. And just like before, the yellow right now is at 83 hertz, and the purple is going to be exactly half of that. And at this low frequency, you can see the LED blinking, and it's keeping up just fine. Now I've got it at about 85 kilohertz, and that is looking really, really good as well. That is a very nice square wave, and I don't see any anomalies on that whatsoever, so it's working really well there. Let's crank that up to 5 megahertz and see what it does. Now I've got that running at about 5.3 megahertz, and kind of like the other ones as well, it looks like it's actually holding up really, really well. It's not really a square wave on the output anymore. It's a little bit more of a triangle wave, but it is definitely keeping up just fine. So let's switch it over to this PWM line with the different frequency and see how it does when we start varying things. Now we're running at around 64 hertz, and we've got the B line, or the second input, varying on a little PWM on a different frequency. That's running at around 61 hertz, where the first input is running at around 63 hertz. And so you can see the output is varying a little bit as those are no longer overlapping perfectly. As we zoom out a little bit, you can kind of see that pattern as it goes through, but it's handling it just fine. Let's kick this all the way up to 5.3 megahertz. Now we've got that up at 5.3 megahertz, and I'll just go ahead and stop that so we can take a look at what it's doing. Let's zoom out a little bit first. And it kind of looks like it did before with some of the other ones up at this frequency. Yeah, it's not really dropping really hard there when that signal goes down, because this should be, you can see it is starting to go down, but it definitely isn't on the bottom. And then it kind of peaked out right there when that other one went ground on channel 1. But kind of interesting. It didn't hold up. This one definitely didn't hold up as well as the AND gate did, but you know, it did okay. And the last chip we've got today is our bonus chip, our NAND gate, our not AND gate. And I've got that wired up, and it's quite simple since it's just got the 2 switches again. Again, I've got 2 switches. The white and the blue are the 2 inputs, and then the blue LED is on the output, which is pin 3. Now you'll notice that it's lit, and the reason it's lit is because both of these are low. So if I take either of these high it doesn't matter. And if I take them both high, then the light goes out. So again, it's that same not and. So it's the complete opposite of the and when it comes to the output. So anyway, that's the not and bonus chip. Let's take this one over on the oscilloscope and see how it performs as well. Now we have our NOT AND gate set up on the oscilloscope. It's set up exactly the same. The top of the yellow is going to be input 1, the pink is input 2, and the blue is the output. And at this frequency, which is roughly 60 hertz, you can probably see that LED blinking a little bit. And if you can't on camera, I can definitely see it in person. And if we look at the logic here, remember this is the NOT and. So when both of them are high, then the output is going to be low, and you can see that tracks perfectly on the oscilloscope at this frequency. So let's increase the frequency and see how it does. Here we have it at about 64,000 or 65,000 kilohertz on the top input, and then the pink input is exactly half of that frequency. And as you can see, that's holding up perfectly as well. Now we have it cranked all the way up to 5.3 megahertz, and as you can see, it's holding up extremely well. So again, when both of them are high, the output will be low. And I'm currently triggering off of the pink one just so that it lines up nicely, and it does work really, really well. So I would say this chip actually outperformed the AND gate from just a pure being able to keep up standpoint. That's a really, really clean output that it has. Let's switch this around to the other timer. So we've got an offset on the two inputs and see how that does. That's running at around 71 hertz, so you can just barely see that LED blinking. But as you can see from the oscilloscope, that's actually handling it extremely well, but that's a very, very low frequency since we just saw that running at about 5 megahertz. So the top channel is around 71 hertz. The pink one is going to be, I'm not sure, I got it zoomed in too far. The pink one is going to be about 61 hertz. And then because it's a PWM signal, we're varying when that trigger hits. And so our output is a little bit off. Therefore, we get a little variation. So let's crank this up and see how it does. And here it is at around 71 kilohertz. It's a little hard to see since it's all over the place. Let's stop that and we can take a closer look at it and see how it's doing. I mean, it looks really, really good. So if we zoom in, we can see where both of them are high, it goes low. We've got some variation on that. So I would say that is still perfect at 71 kilohertz. Let's go up to 5 megahertz. So here we are at about 5.3 megahertz, and it looks like it's keeping up just fine, although no real surprise there. Let's pause it. We can zoom in a little bit on a couple of these little anomaly peaks, but I would say that looks really good from just a triggering standpoint. So at 5.3 megahertz, this chip actually did an extremely good job. So I would say this thing is rated for much, much higher than that. Well, that concludes our look at the and the not and logic chip. So I know that's super interesting, but hopefully you found the work on showing them through the oscilloscope a little bit interesting, and maybe you hadn't looked at anything like a NAND gate in the past. But anyway, that concludes our look at the and or digital logic. There are obviously a few others that we didn't cover, but they weren't in that grab bag. So the next video, I think we're going to switch over to something a little bit more complicated from a chip standpoint, not necessarily from a circuit standpoint. So we'll see how that goes, and we'll see if we can kind of make some of those other chips do some interesting things.